Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is a third video in solving trig equations for trigonometry. The first one we covered how to tackle, or basically the concepts behind tackling trig equations. The second video, which is the precursor to this one, is solving basic trig equations. And now I'm assuming that you've watched that, so we're going to step into higher level equations. These require the use of trig identities for the most part, and so we're going to go ahead and go through these now. So let's start with this first one. Find all solutions to the equation. Notice these are two different trig functions. So how are we going to solve it? Well, as I mentioned in the first video in this series, if you have a mixture of trig functions, there's several different tactics you can use. But if you have a reciprocal function there, you might want to multiply both sides by its reciprocal. So the reciprocal of the secant is the cosine. So I'm going to multiply both sides of this equation by the cosine of theta. This is perfectly allowable as long as the cosine of theta is not 0. So this is a little thing that you have to kind of note off to the side. Note, cosine of theta cannot be 0. The reason why it can't be 0 is twofold. One, we were originally handed a secant in our equation. If cosine is 0, then we have a term that's undefined, because that'd be 1 over 0. So I just want to make sure that in the end that we don't end up with an angle such that cosine would be 0. And if you need to know what those angles are, you can just quickly graph out a cosine function and find out it's pi over 2 and 3 pi over 2. So theta cannot equal pi over 2 plus any multiple of pi thereafter. Pi over 2 plus pi is 3 pi over 2, or plus 2 pi would be 5 pi over 2, and so on and so forth. So I know that I can't have those styles of solutions. The second reason why we have to kind of make that mention why cosine can't be 0 is if it were 0 and we're multiplying both sides of the equation by it, we're basically, you multiply anything by 0, you're going to get 0. You're creating an identity that is always going to be true. So you just have to make sure that what you're multiplying by is non-zero. That's all. Distributing that cosine through, we get 4 cosine squared of theta minus 3 times 1 is equal to 0. There really isn't an identity that we're using here other than the ratio identity, but this leads us to cosine squared of theta is equal to 3/4. If you take the square root of both sides, you'll get that cosine of theta is equal to plus or minus the square root of that 3/4, which is plus or minus the square root of 3 over 2. So we have two equations we're solving now. The cosine of theta is equal to the positive square root of 3 over 2, and the cosine of theta is equal to the negative square root of 3 over 2. Luckily, we have our triangle here. And we were asked to find all solutions. I'm going to do it in radians. The cosine of what angle is root 3 over 2? That's pi over 6. Cosine of pi over 6 is root 3 over 2. Adjacent to pi over 6 is root 3. Hypotenuse is 2. So I know in both cases, my reference angle is pi over 6. Now I just worry about the quadrants. Well, all 4 quadrants are represented here because cosine is positive in quadrants 1 and 4, and it's negative in quadrants 2 and 3. So I basically have all 4 quadrants in play. And now I just list out the solutions. So I have the quadrant 1 set of solutions, which is going to be theta is equal to, with a reference angle of pi over 6 in quadrant 1, you have pi over 6 plus 2 pi k. Quadrant 2, reference angle of pi over 6 is 5 pi over 6, again, plus 2 pi k. Quadrant 3, reference angle of pi over 6, you have 7 pi over 6, again, plus 2 pi k. And finally, quadrant 4. Reference angle of pi over 6, you have 11 pi over 6, plus 2 pi k. Again, in all these cases, k is just an element of the integers. And that is the solution of that equation. Notice, by the way, none of those angles were a pi over 2 plus pi k. So we are certainly safe with those solutions. Next example. Again, a mixture of trig functions, right? You have cosines and sines, but not only a mixture of trig functions, but a mixture of arguments. And that's also a no-no. So we have two issues here. We have different trig functions and different arguments. First thing I'm going to do, and the first thing I recommend that you do as well, is create a different expression so that you can get rid of the different argument. In other words, I want to change that cosine of 2x into something involving only single x's. And we have the double angle identities for the cosine. We have 3 of them actually. Cosine of 2x can be traded out for a cosine squared of x minus a sine squared of x, or it can be traded out for a 2 cosine squared of x minus 1, or it can be traded out for a 1 minus 2 sine squared of x. As I've said in those videos on the double angle identities, this is very much a memorizable theorem. And if you're given those 3 options and you want everything to be the same trig function, I'm going to trade out that cosine of the double angle for 1 minus 2 sine squared of x, so that I only have sines. So that's what I'm going to do here. The cosine of the double angle, I'm going to trade out for a 1 minus 2 sine squared of x minus 3 sine of x, and then equals 2. I will go ahead and subtract 2 from both sides, and then I'll also multiply everything by -1. So multiplying everything by -1, I get 2 sine squared of x plus 3 sine of x. And remember, I took 1 and I subtracted 2 from it, so it should be a -1, but I'm multiplying everything by a negative, so it's a +1. There we go. That should hopefully make sense to you. And now I'm going to see if that factors, and it totally does. It factors to 2 sine of x plus 1 times sine of x plus 1. You can double check my factoring, but I'm certain that's how it factors. And so therefore, either the first factor is 0 or the second factor is 0, because these two objects are multiplying to become 0. So that means that either sine of x is a -1/2 or sine of x is a -1. And we're solving each of those separately. So in the very first case, our reference angle here is going to be a pi over 6. Because again, not looking at the negativity, but just looking at the 1/2, if you paste in our triangle, did I paste it? I don't think I did. There we go. If we paste in our triangle there, you can see, for some reason it's just not letting me tap off of it, that sine of pi over 6 is definitely 1/2. You just get kind of used to going quickly with that. And sine is negative in quadrants 3 and 4. Reference angle of pi over 6 in quadrants 3 and 4. And do we want all solutions? Yes, we do. So the set of solutions from quadrant 3 here are going to be x equals reference angle of pi over 6 in quadrant 3 is 7 pi over 6. And then we have plus 2 pi k. And in quadrant 4, reference angle of pi over 6, we have 11 pi over 6 plus 2 pi k. Those are all the solutions for the first equation, sine of x equals -1/2. The second equation, that's a quadrantal ratio, right? Sine is equal to 0, 1, or -1 means just draw out the sine curve. The sine curve starts at 0, 0 and looks like that and continues on forever. Crosses the x-axis again at 2 pi. Here's pi. But here's 3 pi over 2, and that's the important one here, because at x equals 3 pi over 2, the sine becomes a -1. And so I happen to know that x will be 3 pi over 2, and of course, plus any rotation of 2 pi thereafter. So x from that one is going to be 3 pi over 2 plus 2 pi k. Again, it's any rotation of 2 pi thereafter because this keeps the pattern going. So every 2 pi, it's going to get back to that height. And so we have successfully found all solutions of that trig equation, even though they were different trig functions and different arguments. We were able to use identities, the double angle identities, to reduce it down to a single trig function with the same argument. Now, this is a very dangerous style of equation, and it's also very popular because in trigonometry, and this usually throws people off, so please pay attention here. In trig, you do moves that you would normally do in algebra, but you don't even notice you're doing them. And the moves that you do in an algebra course, you know when to check your work. For example, let me just give you an example here. If I told you you had the square root of x minus 1 plus x is equal to, I don't care, let's say 2 or something like that. It doesn't really matter. You would isolate the radical, right? So you'd say, oh, that implies square root of x minus 1 is equal to 2 minus x, and then you square both sides. Yeah, x minus 1 is equal to 4 minus 4x plus x squared, and then you continue forward. Dot, dot, dot. I just made that up, so there's probably no solution, but whatever. So you go through and you try to solve that. In the end, because you squared, you check your work. That's if you didn't have me for an algebra instructor, then maybe your algebra instructor didn't say it, but they should have, is whenever you square both sides of an equation, you always need to go back and check your work in the end, because squaring both sides of an equation can double the number of solutions that you have. It can introduce what we call extraneous solutions. That all being said, let's go to this guy right here. I have the same trig functions. That's good, cosine and cosine, but the arguments are different. So I need to use a trig identity, hopefully, to trade out one of these expressions or one of these terms. And luckily, we have the half angle identities. The half angle identity for the cosine is as follows. The cosine of an angle over 2 is equal to plus or minus the square root of 1 plus the cosine of the full angle over 2. That is the only identity that I have for that half angle. So that's what I'm going to trade it out for. Go ahead and take that cosine of the half angle and trade it out for this picture right here, which, by the way, has cosine of the regular angle. So that's going to be very nice. I'll just write that in here. This is going to equal plus or minus the square root of 1 plus the cosine of the full angle over 2. And then we have minus the cosine of the full angle is equal to 1. And now you can see why I had that conversation in the beginning about when you have a radical equation and you have to square both sides, you're going to have to check your solutions in the end to see if things are extraneous. Because guess what? We have a radical equation in trigonometry. I'm going to add cosine to both sides to start isolating the radical. So here we go. Implies I have plus or minus the square root of 1 plus the cosine of theta over 2 is equal to 1 plus the cosine of theta. By the way, if you thought you can kind of pass through. This is the problem, I think, when people who don't know, and I'm not talking about you guys, I'm actually talking about when, this is my jab at people who advise other individuals to take courses, when it's their job to advise people to take courses. We constantly see this throughout education, academia, that people who don't deal in the sciences and aren't into mathematics, they just think that you can get through mathematics and kind of not know everything. But the reality is that everything you learn in mathematics gets used in the future, in your future courses, at least in math and STEM. And so if you felt as though when you learned to solve radical equations, you're like, fine, I'll just jump through these hoops, I really suck at this, and then I'll forget about it, it's going to haunt you, because everything you learn continues coming back. So you have to get this stuff down, because it's assumed you know how to solve a radical equation at this point. Anyhow, that wasn't a jab at anybody who's watching this video. It's a jab at people who are attacking mathematics and education and saying, well, students don't need to know everything. It's like, well, then they won't be able to do anything with the mathematics in their future courses, because they won't be able to do the heavy lifting. Anyhow, you don't need to hear my soapbox. All right, we're going to square both sides. Sorry about that. Square both sides. And when you square both sides, obviously squaring that radical, you get rid of the square root and the plus or minus, and it just becomes a 1 plus the cosine of theta over 2. That's beautiful. Squaring the right-hand side, you'll get 1 plus 2 cosine of theta plus cosine squared. Don't make the mistake of saying it's just 1 plus cosine squared. That's bad algebra. So you're squaring the binomial, 1 plus cosine quantity squared. I'm going to go ahead and multiply both sides by 2 because I want to get rid of that fraction. So I have 1 plus the cosine of theta is equal to 2 plus 4 cosine of theta plus 2 cosine squared of theta. And I should note, once I square both sides, I'm going to warn myself right here, check solutions. The reason why is because, again, when you square both sides, you can introduce extraneous solutions. So I want to make sure that in the end, I check my solutions. All right, I'm moving everything over to the right-hand side. So I'll subtract 1 and cosine from both sides. I get 2 minus 1, which is 1, plus 3 cos of theta, and then plus 2 cosine squared of theta, which is totally factorable, but a lot of people don't like to write it this way, so I'm going to write it the other way, 2 cosine squared of theta. You don't have to do this extra step. I have a habit of writing it in decreasing power order. And this totally does factor to 2 cosine of theta plus 1 times the cosine of theta plus 1, which implies that the cosine of theta is either equal to a negative 1/2 or cosine of theta is equal to a negative 1. All right. Now, pasting in our triangle, the cosine of what angle is 1/2? Well, let's see, that's pi over 3. So I know my reference angle for this is pi over 3. And cosine is negative in quadrants 2 and 3. So the quadrant 2 set of solutions would be theta is equal to, let's see, pi over angle, reference angle of pi over 3 in quadrant 2 would be 2 pi over 3. And then we have plus 2 pi k. Make sure, did I want radian solutions or just all solutions? Just all solutions. So I'll stick with radians here. And in quadrant 3, reference angle of pi over 3 in quadrant 3 is 4 pi over 3, and then plus 2 pi k. We'll check our answers in a moment, so I'm not going to box them yet. And then again, we have this negative 1 or positive. If it's a negative 1, positive 1, or 0 for the cosine or the sine, just draw the curve. So here I'm quickly sketching out the cosine curve. Doesn't need to be perfect. I just want to see what input would lead to an output of negative 1. That looks to be pi. So this case, theta is equal to pi plus 2 pi k. Now, before circling things up, you may say, okay, I'm done. But remember, I made that note, check solutions, because we squared both sides of this equation. And when you check your solutions, you do it at the very beginning. This guy up here. So I'm going to rewrite that equation down below, cosine of theta over 2. Let's write it maybe right here. Cosine of theta over 2. And what was the other part? Minus cosine of theta. And it's supposed to equal 1. All right. So let's go ahead and go through each of these solutions one by one. Let's do the 2 pi over 3. By the way, if the 2 pi over 3 fails, then any rotation of that will also fail. So checking, theta is equal to, it's supposed to be equals, is equal to 2 pi over 3. You have to do this. So cosine of 2 pi over 3 divided by 2 is a cosine of 1 pi over 3 minus the cosine of 2 pi over 3. So let's see. A cosine of a pi over 3, we have our triangle up there, is a 1/2 minus the cosine of 2 pi over 3. Well, it has a reference angle of pi over 3, so that'd be basically like a 1/2. However, it's in quadrant 2, so it's going to be a negative 1/2. 1/2 minus a negative 1/2 is 1, and so that checks out. Now we're checking. So I'm going to box this. This totally does work. Now we're going to check 4 pi over 3. Theta equals 4 pi over 3. Now I know what some people are doing right now. Wait a second. What did he just do? He had the cosine of 2 pi over 3 and he made it a negative 1/2. What happened? That's from your work that you've done in Trig up to this point. I just trade out this cosine of 2 pi over 3 for a cosine of pi over 3, but because that's quadrant 2, it's going to be a negative cosine of pi over 3. So it's a negative 1/2. That's what I did. All right. Checking for the cosine of 4 pi over 3. Cosine of 4 pi over 3 over 2 would be cosine of 2 pi over 3. Minus cosine of 4 pi over 3. Let's trade them out for their reference angles. So cosine of 2 pi over 3, its reference angle is pi over 3. But because that's in quadrant 2, cosine will be negative. Minus. Reference angle for 4 pi over 3 is, again, pi over 3. But because this is in quadrant 3, cosine will be negative there as well. And so we have a negative cosine of pi over 3 plus a cosine of pi over 3. That's 0, which is not equal to 1. We want it to become 1. And so that solution here is extraneous. So I'm going to go ahead and take this solution set and cross it out. It's extraneous. It does not work for our equation. So you can see now, when you square both sides of an equation and you have to check all your work in a trig course, there's a lot of extra kind of handwork being done. You have to do it because, well, it's required. We still have to check that pi. The pi should be pretty easy though. So cosine, I'm going to write in here, theta equals pi. We have the cosine of that pi over 2. And what are we doing? Minus cosine of pi. From our picture up above, cosine of pi over 2 is 0. Minus cosine of pi is a negative 1. That's 1. That works. So I'm going to box that up. Go ahead and box that up. And we're done with this solution. We have all of our solutions to this equation up above. It is a lot of work because you do have to check, again, whenever you square both sides of an equation. There's several cases where you have to check all your solutions. Squaring is just one of them. Now here is a daunting looking equation. It does look really, really hard, mainly because of the numbers, but it's also a mixture of trig functions. It's quadratic in form, right? Because it has something squared minus something in the middle, right? It looks like a quadratic equation. But unfortunately, it's a mixture of trig functions. And note, the cosecant here is 1 over the sine squared. The cotangent is cosine over sine, and the cosecant is 1 over sine. So when I see that, and this was again in the initial video in the series where I said if you have a mixture of trig functions, and if some of them are the reciprocal functions, which are the cosecants, cotangents, and secants, then you might want to multiply both sides by one of the base trig functions to get rid of all those reciprocal functions. So in this case, I'm going to multiply both sides by a sine squared. So if I multiply both sides by a sine squared, I'll get the following. 23 cosecant squared times a sine squared just becomes a 23 minus 22 times. Multiplying this stuff by a sine squared, remember there's a sine here and a sine here, they'll cancel. You just left with a cosine. Minus 15 times sine squared is equal to 0. And you take a look at that and you're like, oh, it looks a little better, I guess, but everything's written, we still have two different trig functions. Well, luckily, we have the Pythagorean identities. Whenever I see a sine squared or a cosine squared, I always am reminded of the Pythagorean identities, that the sine squared of x plus the cosine squared of x is equal to 1. Therefore, if I want to get rid of a sine squared, I could trade it out for a 1 minus cosine squared. So I'm going to trade out that sine squared for a 1 minus cosine squared. So we'll have 23 minus 22 cosine of x minus 15, and please use parentheses here because you're trading out a sine squared for a 1 minus cosine squared, and that whole thing is being multiplied by a negative 15. So you want to make sure you keep parentheses on that. Distributing this negative 15 through, you will get, and I hope you don't mind, I'm going to write it in a different order. You will get a 15 cosine squared of theta, cosine squared of x, minus 22 cosine of x. And then you have a 23 here minus 15. 23 minus 15 is positive 8, and that's equal to 0. Not too bad. So, I mean, it still looks pretty terrible, but at least up to this point, not too bad. And I'm going to use the guess and check method really quickly to see how this factors. So I'm going to say maybe it factors to a 5 and a 3. That would give me the 15. And we have two choices. We actually have more than two, but I'll write it this way. Let's see. If it was 5 times 4, that'd be 20, and a 6. There's no way to get 20 and 6 together to become a 22. But if you did 5 and 2, that's 10. 4 times 3, that's 12. 10 and 12 definitely can come together to become a 22. So it's 4 and 2. I'll put a 4 up here, and a 2 here. They both have to be negative. And then we have cosines. Double check my mathematics, but that's the guess and check method. If you have never seen that and you're interested in it, I have a video on the guess and check method. You're more than welcome to watch it. So let's see, negative 12, negative, yep, that's right. So this tells us these two objects are multiplying to become 0. So therefore, either the cosine of x is equal to 4/5, or the cosine of x is equal to 2/3. Now, in this process, by the way, I did not square both sides. I didn't do anything. I did multiply both sides by sine squared. So I could have made a mention that, listen, sine cannot be negative, or 0, I'm sorry. Sine cannot be 0 because we've multiplied both sides by it. However, sine is not going to be 0. I can guarantee that just from these ratios right here. The value that we're going to get for our angle is not going to cause the sine to become 0. Sorry, I had to yawn there. So these are not special trig ratios. And since they're not special trig ratios, we have to grab a calculator. And remember what I said about grabbing a calculator. When you grab a calculator, you're not finding the angle, you're finding the reference angle. So the reference angle is the cosine inverse, in this case, of 4/5. And we know our quadrants, where cosine is positive, are going to be quadrants 1 and 4. And in the other case, our reference angle is going to be the cosine inverse of 2/3. And remember my conversation in last video, if this was a negative 2/3, you would still find the cosine inverse of positive 2/3. So it's just very important to note that you find your inverse trig functions of the positive ratio to find the reference angle. Again, quadrants 1 or 4, just because we are dealing with a positive ratio here. So let's go ahead and go to Desmos and find out what these angles are. Here I am in Desmos and I'm in degree mode. I'm just going to do this whole problem in degrees. And we'll do the cosine inverse, which you have to type in as arc cos in Desmos, of 4/5. And that'll return to us 36.9 degrees. And the other one we had was the arc cos of 2/3. Give our reference angle for the other piece right now. And that's 48.2 degrees. So I'm going to write that in 48.2 degrees. And then from this point forward, you're just going to kind of do the quadrant 1, 4 thing. I do want to mention here, there is a little trick that you can use to make the math much easier for yourself. Rather than saying, well, let me do the quadrant 1 first. Quadrant 1 solution is going to be, well, I have a reference angle of 36.9 degrees. In quadrant 1, that means the actual angle is 36.9 degrees, right? And then plus 360K. But the quadrant 4, if you want to make your life easy on yourself, if you want to make it easy for yourself, you don't have to do 360 minus 36.9. You could actually just say x is roughly equal to negative 36.9 degrees. If I have a reference angle in quadrant 4, that means I've gone backwards by 36.9 degrees. Totally fine. You could totally do that. And then plus 360K. The only thing you need to watch out for is if they ask you, I only want answers between 0 and 360, which they didn't ask here. But if they said they only want answers between 0 and 360 degrees, then obviously you would have to add 360 degrees to negative 36.9. That would give you an angle between 0 and 360. But if they're not doing that, then this is perfectly fine. For the second set of solutions, just as fast, the quadrant 1 solution is going to be roughly 48.2 degrees plus 360K. And the quadrant 4 solution, again, I'm just going to go backwards into quadrant 4. So it's a negative 48.2 degrees and then plus 360 degrees K, where K is an integer. There we go. Not too bad, right? Now this last problem that we're going to do can be done several ways, actually. Multiple ways. I'm going to do it the way that you would do it in Trig, and then I'm going to speak to my pre-calculus students, because when you're in pre-cal, you review all this stuff, and then you do a little bit more on top of it. And the little bit more is kind of powerful in this case. So if you want to pay attention to that part, you're more than welcome to. But we're being asked to solve this equation on the interval 0 degrees to 360 degrees. We have two different trig functions, the sine and the cosine. And unfortunately, neither of them is squared. And so we are going to stare at this dumbly for a while and say, wait, how do I transform one of those into the other? It's pretty much not impossible, but very, very challenging to do. It would be slightly easier if the right-hand side wasn't 1, but instead 0. However, it's not. So this is what we're stuck with. So one thing you can do is isolate one of those and square both sides. And that's probably the first way I would teach this. I would say, well, just isolate the sine. So sine of theta is equal to 1 plus the cosine of theta. And then square both sides. Now remember, when you square both sides of an equation, you are likely introducing extraneous solutions in addition to finding the actual solutions. So you'll have to check your solutions once you square both sides. So that's what we're going to do here, though. Take this guy and then square both sides. I get sine squared of theta. Oh, by the way, you might be wondering why I'm squaring both sides. It's because when you square a trig function like the sine, you get an identity, which allows you to rewrite that square in terms of the cosine, which would then put us all within the same trig function. But I'm going to make a little note because I squared both sides. I'm going to tell myself to check solutions in the end. All right, let's move forward. I'm going to take that last step, and I'm going to use the fact that sine squared is 1 minus cosine squared to rewrite that. So 1 plus 2 cosine, and then plus cosine squared. And now I will just go ahead and add cosine squared to both sides and subtract 1 from both sides. And I'll get 0 is equal to 2 cosine of theta plus 2 cosine squared of theta. And now you can see both those terms have a cosine and a 2 in common. So I'll go ahead and factor that out. It's equal to 2 times the cosine of theta. And when I divide that off of both those terms, you get 1 plus a cosine of theta. And of course, that implies that either the cosine of theta is 0 or the cosine of theta is -1. And I'm just looking to see what we're solving on, 0 to 360 degrees. So let's go ahead. These are quadrantal ratios. I'm just going to quickly sketch out the cosine curve off to the right here. Looks like this. From 0 to 360 degrees. Nobody would ever, you probably have never seen somebody write the degrees on the x-axis. It's because, honestly, we would never really truthfully do that. However, in this case, we kind of have to because they're forcing our hand by saying answer in degrees. So such is life. But normally your x-axis would never be in degrees because it's just too broad of values. 360 pips along the x-axis just for a full cycle is ridiculous. Anyhow, cosine, you can see, becomes 0 at 90 degrees and 270. So theta is equal to 90 degrees or 270 degrees. And then cosine is equal to a -1 at 180 degrees. Now remember, I squared both sides early on, so I have to check my solutions. So I'm going to go back to the original problem and plug in 90 degrees, 270 degrees, and then 180 degrees. And just for our purposes, I'm going to draw out the sine curve. There's 360. Terrible handwriting, I know. 180 degrees. Here's 90 degrees. And here's 270 degrees. All right. So checking. For theta equals 90 degrees, and remember our equation was sine minus cosine is equal to 1. We want sine of theta minus the cosine of theta to equal 1. Well, at 90 degrees, sine of theta is 1. You can see it up above right here. So we get 1 minus, and cosine of theta is 0. That works. So I'll keep the 90 degree. At 270 degrees, let's see, 270 sine of theta, sine of 270 is -1. Cosine of 270 is 0, which is not equal to 1. So I'm going to throw out the 270 degree angle, and then I'll check the 180 degree angle. Sine of 180 degrees is 0. Cosine of 180 degrees is -1. So 0 minus a -1. That's 1. That works out. So 90 and 180 are our only solutions. I'll box them up. 90 and 180. That's a good example. Very complex just because you have to square both sides to get that Pythagorean identity in there. Now, I want to talk to pre-calculus students for a moment. If you're in pre-calculus, you should have recently watched a video on how to combine sines and cosines. Now, if you're in a trig class, you're more than welcome to watch this. I'm just making some room off to my side here. Boom. All right. So what can you do? Well, remember, if you have a times the sine of theta plus b times the cosine of theta, you can rewrite that as the square root of a squared plus b squared. So I'm going to just say this is the same thing as the square root of a squared plus b squared divided by a square root of a squared plus b squared. So really you're just multiplying by 1 times a sine of theta plus b cosine of theta. Distributing the denominator through, that would give you the square root of a squared plus b squared times a over root a squared plus b squared sine of theta plus b over the square root of a squared plus b squared cosine of theta. Now, obviously, if you've already done this style of problem, you don't go through all this. It's very fast, actually. But the idea is still there, that you want to normalize those coefficients and then trade this out for the square root of a squared plus b squared times the sine of theta plus phi, where the cosine of phi is a over the square root of a squared plus b squared, and the sine of phi is b over the square root of a squared plus b squared. So that's what what you should have learned in your pre-calculus course at this point. So that all being said, normally you wouldn't even bother like writing that stuff out. You would just look at this statement: sine of theta minus cosine of theta is equal to 1. So let me just start it as if I'm in pre-calculus. Sine of theta minus cosine of theta is equal to 1. Well, I'd love to imagine that there's a coefficient on this sine. There is, it's 1. There's a -1 on that cosine. But the coefficient on the sine is related to the cosine of a different angle. And the coefficient of the cosine is related to the sine of that very much same angle. So I'm going to just mention cosine is always related to the horizontal side of a triangle, at least when you're drawing on axes. And the sine is always related to the vertical side of a triangle when you're drawing on axes. So where is our horizontal side positive? And where is our vertical side negative? That would be quadrant 4. So let's go ahead and draw a triangle in quadrant 4. There we go. Where the adjacent side is 1 and the opposite side is -1. I will call this angle phi, and you can see that this is a square root of 2 because it is the 45, 45, 90. In fact, easy to see, this is a -45 degrees. Now, I don't know if we want to answer in degrees. Yes, we did. It's a -45 degrees. Okay, great. So again, if you've already done this, it should be literally this simple. That equation can be rewritten as the square root of 2 times the sine of theta plus the negative, or in other words, minus 45 degrees. And that should equal 1. Okay, well, let me divide both sides by the square root of 2. So we have sine of theta minus 45 degrees is equal to 1 over root 2. And now I can say, well, what is the reference angle? Well, the reference angle, theta minus 45 degrees hat, is 45 degrees. That's what you would normally plug into the sine to get out an output of 1 over root 2. And sine is positive in quadrants 1 and 2. And so therefore, theta minus 45 degrees should equal, well, in quadrant 1, 45 degrees. And in quadrant Let me put quadrant 1 here. In quadrant 2, theta minus 45 degrees. Let's see, we have a reference angle of 45 degrees. In quadrant 2, that's 135 degrees. Now add 45 degrees to both sides of each of those equations, and you'll get theta is equal to 90 degrees, or theta is equal to 180 degrees, which are the two solutions that we got previously. Somewhere. Right up there. We boxed it up. So that is a way you can do it if you've had pre-calculus and you know that that formula to condense the sum of a sine and a cosine into a single sinusoidal function. That is incredibly useful for differential equations and signal processing, because you really can talk about amplitudes and phase shifts and stuff like that very easily when you have a combination of sines and cosines and you compress them into a single sinusoidal function. Anyhow, that's only for those who have gone through that. That's not if you're in a strict trigonometry course. It's only for pre-calculus students. All right, we're done here.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.